In this example, again, we will find the currents by applying the Kirchhoff rules for a multi-loop circuit, like in this picture. But this time we have a capacitor which is connected to one of the loops. And for a circuit, if it has a capacitor, then the current is changing in time for a certain period. But after a certain time, the current flowing through the capacitor will not change, and we call this situation the steady state, and we will see what the steady state for an electrical circuit. As I said, when there is a capacitor in a circuit, the current is not steady, it is changing over time. It will decrease for some time, but after some period of time, the current will no longer change and the circuit will reach a steady state condition. Basically, steady state condition means that if the physical parameters in a system does not change over time, then we call this steady state. If, for example, if you have a time varying currents in a system, in a circuit, then that means you haven't reached the steady state condition because the currents are changing. Well, let's think about this capacitor. If you think that a capacitor is connected to a battery, what happens when you close the circuit, when initially the current will go through the capacitor? Well, what happens inside a capacitor, if you have an initially uncharged capacitor, when you connect to a circuit, of course, the battery in the circuit will start charging the capacitor, right? If you connect, for example, the capacitor in this branch to a battery like this, then the plus side will induce a current through the plus side of the capacitor. That means this side, this plate of the capacitor will get positive charges because it is connected to the positive terminal of the battery. But this charging will not continue indefinitely. The capacitor, of course, will not collect charges infinitely. It has a capacitance, after all, that's the name for it. It has a capacity to hold a certain amount of maximum charge. And the capacitor has reached this maximum amount of charge, then there will be no more a current flowing through the capacitor. So the current will stop, and then the current will be zero when the capacitor has fully charged. Okay, so this is the case in here. When you have this multi-loop circle, and on this branch, where the branch has B, A, H, and G, on this loop or the branch, after a certain time, when the capacitor is fully charged, there will be no current flowing, and we have already denoted this condition in here by putting the current on B, A, H, and G is equal to 0. So the current on this branch at the steady state for this multi-loop circle is 0. Why? Because after some certain time, after a long period of time, the capacitor will be fully charged, and there will be no more charging. That means there is no more current flowing through the capacitor. Well, by setting this condition, then we are ready to apply the Kirchhoff rules to our multi-loop circle. So we start with, let's say, junction C, and of course when you put I is equal to 0 for this branch, then there will be three different currents flowing on this multi-loop circuit, and let's assign these current directions and names like this. For example, on this branch between B and C, let's label current as I1 and choose the direction like this. Okay. Well, setting the directions is initially not very important. It's all totally up to you, because once you set up everything, the directions and everything, and you apply the Kirchhoff rules for the junction rule and the loop rules, whenever you find the values of these currents, if you find, for example, a negative currents, that means the directions that initially you have chosen will be reversed. Okay, so there is no problem in choosing in any in what direction. It's totally up to you, as long as you have a junction on which all the currents are incoming. This is not an acceptable situation. So you choose the direction so that some currents are going into junction and some of the currents are going out of the junction. So let's choose these currents, like for C, the junction C, I1 is coming and I2 is coming from this branch and I3 is going out from the junction C. So, well, if you have chosen I1 for this branch, and if this part of the circuit is open circuit means there is no any current flowing, so you can ignore this part. That means if you have chosen I1 in this direction on this part, then the same current I1 will flow in this direction on this branch between B and G. So, and also since this is the same cable and there is no diverging or any junction on this part, if you ignore of course this part because there is no current flowing on this part, there will be the same current I1 flowing from F, G, B to C. Okay, so the current flowing on F, starting from F, G through B and C, is the same current, and we label this as I1. So I2 is only flowing on this middle branch, the current flowing through the 3 ohms resistor between F and C, and I3 is flowing between on the rod C, D, E and F. So all this branch contains only one current, and this is I3, and it flows through 5 ohm resistors, also flows through 4 volts battery. So the first rule of the Kirchhoff's is just find as many independent as junctions you have in the multi-loop circuit, and then write down the junction rule on which the total incoming currents is equal to the outgoing current. So this is the rule for junction C. Next, let me label this equation as 1 because we will use this later. So let's choose next the loop D, F, E, F, C, D, which means here on this picture D, you start from D, go in this direction, crossing the battery from minus to plus, come E, and there is nothing in between E and F, and from F you go towards C, crossing this 3 ohms resistor, and from C you go in this direction, crossing the 5 ohms resistor, and come to the D, the same point, the same starting point. So let's apply the rule, the loop rule. You start from D, and since you are going in this direction, okay, you are going in this direction, you're crossing a battery from minus polarity to plus polarity. That means you will take the battery value as plus. So you put just 4 volts. And you go, there is nothing in here, and come to F. From F you go in this direction. You're going, since you are going already assigned in the direction of assigned current value I2, that means you will drop the potential by crossing this 3 ohms. So you have to subtract from 4 volts this 3 times I2, 3 ohms, the value of the resistor times I2. So you continue and come to C. From C to D, on the way we have this 5 ohm resistor, and our traveling direction is in the same direction with the current I3. That means again you are lowering your potential from crossing from this side to the other side. That means you again subtract this value 5 times I3. Okay, so you come to the same point D, and then all these sum or change in the potential will be equal to 0. This is the second rule of Kirchhoff's for loops. Of course, since we have 3 independent currents, that means we have 3 independent variables. To solve these 3 independent 3 unknown values, we need at least 3 equations. So This is the second equation, and we need a one more loop equation that let's choose for that third loop. As C, you go in this direction to F, and you go to G from here to B, and from B you come over the same point again, C. So we choose this loop in this traveling direction, okay, in the clockwise direction. You are going in the clockwise direction, and at some branches you see you are going opposite to the current, and some branches you are going with the direction of the current. So let's start with the point C and the traveling direction. Since the traveling direction is the clockwise direction toward F, you go in this direction on this branch between C and F. But on this direction, you cross the 3 ohm resistors, but you're going in the opposite way to the current that you initially set up the direction, I2, you are going in the opposite direction. That means since you are going in the opposite direction when you're crossing a resistor, that means the change in the potential is plus, not minus, because if you were going in the same direction with the current, then the potential will be lowered. But since you are going in the opposite direction, this is the rule, and you will put this plus value 3 times I2. Okay, so from going from point C to F, you increase the potential. That means since you are taking a plus value, you're increasing, you're going to a higher potential point. All right, so let's continue from F to G, and again we have another resistor, 5 ohm resistor, but this time you are going with the direction of the current I1, which has already initially set up the direction. Since you are going in the same direction with I1, and the rule says if you are going with the same direction with the current, and then you are crossing a resistor, that means you are lowering your potential. That means you have to subtract this value 5 times I1 for this part of the circuit. So minus 5 times I1. Now continue from G to B. Doesn't matter in which direction compared to the current, since you are crossing a battery and you are crossing the minus polarity to plus polarity. That means you are going from the lower potential to the higher potential. So you will add this EMF of the battery 8 volts as plus to the equation, and you come next to the same point C. So this will be the third equation coming from this loop, the second loop, and this will be equal to 0. So this is our third equation. So now we have 3 equations with 3 unknowns, I1, I2, and I3, and we all know what the values of the resistors are, so the rest is just algebra. And for this you can put, for example, the first equation into second equation. That means you replace I3 by I1 plus I2. If you do this, then you will have 2 equations with 2 unknowns, I1 and I2. These 2 and 3 equations will contain only I1 and I2 because you already replaced I3 by I1 plus I2. So you have now these 2 equations. These 2 equations, right? This is a modified equation from 2, and this is the third equation. Well, if you add these equations side by side, you see there is on the left hand side on the first plus 5I1, and on the left hand side of the second equation we have minus I1. So if you add these 2 equations side by side, you will get you will eliminate these I1 terms. Then you will be left with only I2. Well, in that case you will have 1 equation with 1 unknown, so it is very easy to find I2. You see, you find I2 as a negative quantity. It's 4 divided by 11, minus 4 divided by 11, and it is minus 0.364 amperes. So that means since you find a negative quantity for I2, that means the direction that you have already set up initially for I2 will be reversed. So the actual direction for I2, the current between C and F, will be from C to F, not from F to C, which you already initially chosen for I2, but it will be in the reverse direction because you have found in negative. But the value, the strength of the current will be the same. So you don't worry about the changing the strength, but only you will change the direction. Okay. So next, it's easy because you can put this I2 into one of the equations in here to find I1, and you find I1, and when you find I1 and I2, it is one step away from finding I3, so you get I1 as 1 plus 1.38 amperes, okay, and I3 is 1.02 amperes. These are both positive quantities, so that means whatever the directions you already initially set up for I1 and I3, they will be the same directions, so there is no need to change the directions of these currents. So the directions will be the directions set initially for these currents. Well, we are done with finding these currents, but there might be one question about this capacitance, right? Well, since there is no current flowing through this capacitance and also the battery, next question might be, well, there is no current flowing through this capacitance because the capacitance is fully charged, but the question might be, what is the charge then? Okay, so if this capacitor is fully charged, the capacitance is given as 4 microfarad, and you may wonder what the charge on this capacitor. Okay, for this, whenever you have a capacitor and if you know the capacitance, you can get the charge on the capacitor if you can find the potential difference across the terminals of the capacitor, because from our the knowledge of the capacitors from the previous chapters, we know that the charge on one of the capacitor is nothing but its capacitance C times voltage across the terminals of this capacitor. So if we can find the voltage across this capacitance, then we can find, by multiplying this voltage difference by 4 microfarads, I can find what the charge is. Okay, so for this, think about this loop. Okay, even if there is no current flowing through one branch of a loop, you may still apply the Kirchhoff's loops rule. So just choose this loop which contains the capacitance B, G, H, A, and B. So this loop, we are using the loop rule for this closed circuit. Even if we don't have any current flowing through this, we may apply the Kirchhoff's second rule to this loop. So let's see what happens then. Okay, so if you start from B in this direction, because we have already chosen this clockwise direction for the loop, we are going from plus side of this battery to the minus, so this minus 8 volts, and you are going now here. Okay, so we are here, all right, we are crossing through a capacitance, and the capacitance has one plate a negative potential value, and the other plate is at the positive potential value, because the capacitance is already charged. So you are crossing from minus to plus. That means you will add to this equation the plus, the difference between these, the difference in the potential difference between the minus and plus terminals. This is a positive quantity because you are crossing again a capacitance from minus to plus side. So you add the potential difference between the terminals of the capacitor as V cap, that means the potential difference between the terminals of the capacitor. You continue after this, crossing this battery from plus side to minus side. That means you have to subtract this value from the equation, so you add this as minus 3 volts and come to the same point, and this will be equal to 0. So you see we have a formula, an equation for this loop we already chosen, including this capacitance, and we have inside this equation the voltage across the terminals of a capacitor. So this solving this equation for V capacitance is very easy. It is just when you solve this, you find the voltage difference between the terminals of the capacitor. You find 11 volts, and since you are given the value of the capacitance as 4 microfarads, the only step you are away from finding the charge is just multiply this capacitance C with the voltage difference that you just found, and you find this as 44 microcoulombs as the charge which is on this capacitor at the steady state, because there is no change anymore on the charge, and this charge is maximum for this capacitance. And we have already applied the Kirchhoff's loops rule to find, even there is no current through this branch, we are able to find the charge on the capacitance by just applying the Kirchhoff's rules.